Do you can remember the extreme value theme for a function of one variable?
What does it say? It says that if a function, if it's continuous on a closed interval, okay, let's think about this one. So you have a closed interval, a to b, it is closed. And the function is continuous on it, on this closed interval. This function f, the function of one single variable, then guarantee that that is at least one absolute minimum and one absolute maximum this function is going to attain on this closed interval. Now, looking at this one here, you know that the maximum value occurs over here. The minimum value is going to occur. I'm going to change this a little bit. So I'm going to. Okay. So we actually get the maximum value here, and then we also get a minimum value over here. So the maximum and minimum, they are going to be guaranteed if we have a continuous function on a closed interval. Okay, that was the extreme value thing. Okay, the maximum minimum can occur inside the interval or sometimes at the endpoint. Okay, it could happen that way. And at that time, we also did the closed interval method. Okay, do you guys remember closed interval method? This is the Mach 110A closed interval method that I taught. Okay, at that time, I told the student, you always think about what's the domain first. Get the domain here first. If it's a closed interval, then you think about it's a closed interval method. Okay, so if they give you a closed interval, then you will restrict the domain to that closed interval there. And then the second step, you take the word t to find critical number. You set that equal to 0 or does not exist to find those critical number, and see if they're in the domain. See if they're inside this closed interval. And if they are inside the closed interval there, you're going to put them, you can make a table. Right here, put all those critical numbers here and here. And you also put the n, this n on this side and this n on this side. So put the two n over there. Because extreme value can happen also at the end or at those critical number. Those are the only possible places for extreme value. So we're going to consider critical number and also the n. After that, you will substitute those x value and you just compare the function value at all those. Whatever that's highest is the absolute max. Whatever the lowest is the absolute mean. So that was a closed interval method for function of one variable on a closed interval. I call it CIM, okay? So it's not CIA. Okay, now go back. Well, at that time, we need a closed interval, right? But then how about in two-dimensional case? In two-dimensional case, we need to think about closed set. Okay, instead of the closed interval, we think about closed set. So what's the definition for a closed set? Look at some example here. These two are closed set. All these three on the right side here, those are not closed. Okay. Closed set here will include here's a definition for the closed set is that contain all of its boundary points. See, all the points on the boundary, they are included. This one here is not closed. The boundary here is dash, so it doesn't include the boundary. This one here includes almost all of the boundary except just one single point. It missed one single point. Then this is considered not closed. If it misses just one single point, that's not closed. This one here is not closed because missing this boundary here. Okay. So those are the closed set. A bounded set in R2 is one that's contained within some disk. Okay, and then another definition here is talk about a bounded set. Okay, so what does a bounded set? That means you can contain. Okay, so suppose we have a set over here. Okay, so we have a set like this in R2. Okay, then how is it bounded? Well, if we can contain this inside some disk, then this set over here is bounded. Okay. Now we have this extreme value theme for function of two variables. Okay, so very similar to the one we had before. So if a function is continuous on a closed bounded set in R2, then the function attains absolute maximum and also absolute minimum some point inside that set, right? Do you see the connection between similarity between this one and the extreme value theorem for the one-dimensional case? So the one-dimensional case, you have continuous function, okay? One-dimensional case, you have continuous function on a closed interval, right? Then you get maximum, minimum. Over here you have continuous function on a closed bounded set, something like this. Then the function attains absolute maximum, minimum, okay? This is a set right here. This is a closed bounded set. All right. Now, how do we find that? To find this one here is kind of similar to the closed interval method, okay? So we just went over the closed interval method. Here the step over here. So you find the value of the function at what of the function in D? Think about what should I put over here? At the what? One dimensional case, those are the critical number. So this case here will be what? There will be critical points, right? Those critical points of the function. Okay, so say like this one, because I will try to recall my voice when I speak it. But think about this, okay? This one here, for one-dimensional case, you look at the function value at those critical numbers and also the endpoint. So for that, the other one, function of two variable, you look at the function value at critical point and also the endpoint, okay? And the boundary, okay? So this one looking at the critical number and also at the endpoint and see the function value. For that one, we look at the critical point and also the boundary. Okay. So, and see what happened to the function. Okay. So critical point and also the boundary. We look at the function value over there. And then just like what we had before here, you're going to compare those function values. Whatever is the highest is the max, absolute max. Whatever is the lowest is absolute mean. Then similar to this one. So you're going to compare those values at the critical point and also boundary. The absolute max will be the highest and the lowest one will be absolute mean. Okay. So let's try to find
the absolute max and mean values of the function on this rectangle.
I draw the rectangle over here. Is this pink rectangle? Okay. Is this a closed bounded set? Is it closed? Does it contain all of the boundary? Yeah. It is bounded, right? You can contain that in some disk. Okay. So it's a closed bounded set. So, and is this function here continuous function? Yeah, it's a polynomial function. So continuous function on a closed bounded set, I know that it must attain max and mean, right? So we just need to find the max and mean. So how do we find that? According to the closed, kind of similar to the closed interval method, what do? We look at the function value at where? At number one will be critical point, and also number two will be at where? Boundary, right? At the boundary, okay? So two things. So you're going to look at the critical point and also the boundary.
Similar to this one, you look at the critical numbers and also the end.
So let's look at the critical point. Let's find the critical point here first. We know the boundary, right? Those are the boundary. Okay. So how do we find critical point? We take partial duality and set that equal to 0. Okay. So we first find critical point, and that occurs when the partial duality equals 0. So I took the partial duality here and here and set that equal to 0. Can you tell me what does x equal to and y equal to? From here, x equal to what? 1, right? X equal 1. And then substitute 1 here, y equal to? Is it also 1? Right? Okay, so that's 1, 1. And now we're going to find the function value at this critical point. Okay, substitute x to be 1, y to be 1. So you have 1 minus 2 plus 2. So that's 1, right? So the function value is 1. So keep that in mind. Okay, so what do we have here? I'm going to actually label this at 1, 1. So at here is going to be 1, and here is going to be 1. So at this 1, 1 over here, okay, so at this 1, 1, this is the critical point. The function value is 1, right? So I know that it is 1. Function value is 1, okay? So that's the critical point. So what's the next thing to do? The next thing to do here is we try to look at the function value where? At the boundary, okay? So, and see what happens. So let's look at the boundary function value. Look at the function value on the boundary of the set. Well, it has a couple line segments, 4 line segments, okay? It is this line segment L1, L2, L3, L4. And we have to consider each one of them separately, okay? Let's consider L1 first. Okay? So on L1 over here, this is on the x-axis. So y will be equal to 0. And that was the function. So when you set y equal to 0, this 2 will be equal to 0. So the function will be equal to x squared along this x-axis. Okay, and x is greater than equal to 0 and less than equal to 3. So the smallest value over here will be what? So square, which is what? 0, right? And what's the highest value along this? 3 square, which is what? Which is 9, right? Okay. All right. So we know that along this boundary over here, the smallest function value is going to be 0, and the highest function value is going to be 9, because this is x squared. X go from 0 to 3, then y go from 0 to 9, right? Okay. Okay, so we keep that in mind, okay? So 0 and 9. The smallest 0, the biggest 9. Okay, now we're going to do along this boundary, L2. Along L2, what's so special about L2? L2 over here, the x coordinate is always 3, right? It's always 3. Now you're going to substitute x to be 3 here. And that is going to simplify into this function. And notice that y here changed from what? 0 to 2. When y changed from 0 to 2, okay, the smallest value will be 1, and the highest value will be 9. Okay, when y equal to 0, 9 is the maximum for this one. Okay, so along this one, this is the highest, this is the lowest. And then similarly, you can do it for L3 here. And for L3, the y coordinate is 2. The y coordinate is 2. So you substitute y to be 2. And then you found this max and mean. Okay, you found the max and mean for that. And then also on L4, you find the max and mean. Okay. So, but because all of those are either horizontal or vertical line segment, you're going to fix one of the coordinates, okay, and then substitute to find the max and mean. Okay.
So here I enter all the extreme value along each line segment. So 0 and 9, 9 and 1, 0 and 4, 4 and 0. Those are the extreme value along each line segment.
Now remember, we can just compare and find the absolute max, right? What's the absolute max? 9. Yeah, 9 is the maximum value, right? What is the absolute mean? It's going to be 0, right here and here and here, right? So we have absolute max to be 9. It occurs at over here. And we have 0 as the absolute mean occur here and then here, these 2 places, okay? So this is what happened. And here is a graph for, here's the graph for this function, okay? Now what do you see here? You see 0, 0. Okay, what do I have here? So the minimum is going to be 0, okay? And you see on this box over here, on that rectangular box there, 0 is the minimum here and here, okay? And 9 is the maximum that occurs over here. And then this is the ground of that one. All right, so this is the end of this section.